code to edit images today. And I'm Kevin.
And I'm Sachin, and we're grad students at UMD.
Yeah. Okay. So the first thing is like, how do we make images, right? Like how do we like make JPEGs? And so the way this works is you can think of it as there being like three components to a camera. So the first component on the front is the camera lens. So the camera lens focuses light onto the second part of the pipeline, which is the image sensor. The image sensor takes that light and then basically converts the light into electricity, and the electricity gets digitized into like ones and zeros, into binary things a computer can understand. And then once it's in that form, then the last part of the pipeline is the image processing pipeline, which takes those ones and zeros and then basically turns it into like a JPEG that we're all like pretty familiar with. Right. Okay. So let's go over the first part of the pipeline. So what does a lens do? So like glasses, lenses just focus light. So if you imagine like light hitting the object, and then it bounces off the object, it hits the lens, and the lens focuses the light points onto the sensor, and the scene is like nice and sharp, and then the sensor converts the scene into like it converts the light into electricity. And then how does the imaging sensor work? So this is a very high level overview. So you can think of like an imaging sensor as like an array of photon buckets. So like they're just like a bunch of little buckets. And then you can like think of the photons almost like raindrops, right? It's like raindrops falling into a bucket. And then like the value of each bucket is how full the bucket is, like how many photons have like dropped into the bucket in a given time interval. And then the buckets essentially just count the number of photons and then turn that number into like an electrical signal. Like it gets turned into a voltage, and the computer can like process the voltages because the computer is just designed to process electricity. And the last part of the image formation process is the image processing pipeline, which is the one that we're going to focus on today. And so this is the stuff where, okay, now you have like ones and zeros, you have like this binary representation of the image, and you want to like do stuff to it to make the image like nice and appealing. And so let's delve a little bit more deeply into what happens in this last part of the process. So like we discussed before, there's an illumination source. So this is like maybe the sun or something. This is the object in the scene. So light goes from the sun, bounces off of the scene object, hits your imaging system, which is like the camera and the optics we discussed before. And then an image gets formed of the image plane, which is like the sensor grid. And this is where like the discretization happens. So, objects are like smooth and continuous, but as we all know, computers, they operate on like very discrete objects. They operate on ones and zeros. So you have to like discretize the image into a grid. And so when you take a picture of something, what that means is an image on your computer is just like a grid of values, right? So everywhere where there's like white, where there's no value, or everywhere where there's white, where there's like a lot of light, you can think of this as like a 1. And everywhere where there's black, you can think of this as like a 0. And then the grays are somewhere in between like 1 and 0, right? But this is all grayscale. But humans see in color. And humans have like 3 types of color cells in their eyes, so we're sensitive to like mostly 3 types of colors, like RGB. And so images are stored on the computer in a very similar way. You have like 3, we call them color channels. Each one represents like how much red, how much green, and how much blue is in an image. And once you put all of these together, you get a nice like full color image.
Yeah, so now we're going to talk about how to process these types of images. So recall we have a 2D grid of a bunch of values, and we happen to have 3 of them for red, green, and blue. And we can basically do math operations on these values to affect the image in different ways. So a very simple operation we can do is nothing, right? We can just take the input and output. And so we produce a nice picture of the baby like that. But maybe we don't like this image. We want to maybe darken it. So we could subtract, for instance, a value from it, and overall the image gets darker because instead of recording a high intensity value, we're artificially decreasing it for every value. Now, similarly, this kind of uniformly darkens the image, but maybe you want to increase the contrast between lower the contrast between different parts of the image. So we can, for instance, divide by 2 and end up with that looking baby. But now there's all these other sorts of things. So I guess as a question to the audience, does anyone have an idea of how to implement any of these other ones? You can arbitrarily pick. if you'd like, or not, that's okay too. So and anyone know? Okay, so for nonlinear lowering the contrast, we can apply this, which is basically first. So I guess we didn't quite discuss this earlier, but generally computer stores the values from 0 to 255 because it can be represented by 8 bits. So in this case, we're taking the value in a pixel, we're dividing it by 255, so we get a value from 0 to 1. We're taking the cube root of it and then remultiplying by 255. And this is a similar to just dividing in the first place, but it has like nonlinear effect because it's the cube root in there. Now, to invert an image, we can just take the max value and subtract x. We can lighten the image by doing the opposite of darkening it, right? So we can add 128 instead of subtracting. To raise the contrast, we can multiply instead of divide. And then non-linear raising the contrast is, instead of taking the cube root, we now square it. So these are all examples of simple math operations you could do to the pixel to end up with these effects. So now we're going to have you try to do these things. So if you want to, if you have your laptop, you can go to this tiny URL or scan the QR code. I'll give people a chance to do that. Yeah, I'll lead you to a link.
It'll lead you to like this web-based code editor that you can use to like play around with the concepts here. No,
You can do it on the
You're
computer.
supposed to. You're supposed to just go to the URL.
Yeah, go to this URL in your browser.
Yeah, we'll also like switch to the.
So it should look like this when you're done. Yeah, it's tinyurl.com/DIY-Photoshop. Oh, is everyone good with this? Have the link? Okay, then so it should look something like this. And I guess if you are so if they'll have a button like this, copy to drive, at the top corner, like up here, it'll say it. And so you want to click that so you can start editing it. But it'll look like this. And what this is an online environment to code in Python. And we have a bunch of like pre-made code in here that we'll use throughout this demonstration. So the basic setup of how this works is there's a bunch of what we call cells. And next to the cells that have code in it, there's this little play button that you can click and it'll execute whatever's in that cell. So this very first one, if you click play, it will download the images that we're going to use to process. You're also welcome to upload your own images by clicking this little files thing in the corner, and then this upload button right here. And then you can select something from your computer. But you can also just use the ones we gave you. We gave you a picture of the CS building, which is the AREE building, and a picture of space, if these will load. Okay, then then we'll keep on going along. If people have questions, like feel free to shout out. But so the next thing we'll do, we're going to import a bunch of packages that we're going to use to do a lot of these math operations, so we don't have to do everything from scratch. The next step is now we're just going to open these images so you can see what they look like. So if people want like a brief explanation of this code, there's this package called OpenCV that provides a lot of these like image parsing things. So we're reading the image in, and then we're converting it to also to grayscale. So you can see the idea of you can have an image with RGB channels and also just a gray one. So this is a very simple thing, not too involved here. Everyone good with this? Nod, yes, cool. Okay. Now this next cell is just making things smaller because otherwise, processing is quite slow, and this image was like as a very high res image, so we're going to make it a little bit less high res. And then this is where now the exciting part comes. So if we go back to the slides real quick, right? These are a bunch of different ways you can do point processing on an image, right? So pixel-wise math operations. And what we've done is we provided you the first two. So we have the original image, which is just the identity. And then we have a function that darkens the image. So it subtracts that 128 value from it. So if we run this and then you run the next cell, it should produce something that looks like this. And you can see we have darkened, but the rest look like the original. And so the goal now is to produce something that looks like this table. So something that lowers the contrast, does nonlinear, lower contrasting, inverting, lightening, etc. So you can add your math functions in each of these different places. Does that make sense to people, or people need more? Yeah. So okay. So we'll give you a few minutes to see open-ended play around, see what happens. You can do one function at a time, all of them at once, and then override hints towards the end.
Yeah, we should probably leave it up here. These are the formulas.
Okay, do people want more time, or do you want us to kind of go through now and go through the functions? More, that thumbs up more time, or go through the functions? Okay, great. Okay, so I guess, do people want to shout out the answers for some of these? So how can I lighten this image? No one knows. Let's go back to the slides. Yeah. So, oh, so for invert, you're saying? Yeah, so you're saying, what should I do? I should subtract from the image. And what should I subtract from the image? To invert the image. Let's go back to the slides real quick. So we're trying to accomplish this. So in this case, we want to do the opposite. We want to take the maximum value 255 and then subtract the image. So if we run this, you can see now it inverts it. Okay, so these rests, yeah, so we'll quickly go through them. So lightening the image is the opposite of darkening. So instead of subtracting, you want to add. To lower the contrast, it's dividing by 2. And to raise the contrast, you want to do the opposite, so times 2. And quickly see the effects of those. Right, so we've darkened the image, we've lightened the image, like it's probably not great, but we've raised the contrast, we lower the contrast. And now for these nonlinear ones, these might be a little bit more tricky because they involve a power. But so first we'll divide the image, then we'll raise the contrast. And this star here, that means power, like exponentiate. So this is like x to the 1/3, which is the cube root. And then we will multiply by 255. And then similarly,
but you need to multiply by 255 here. We divide it twice.
Yeah. And and huzzah. So, a similar form of raising and lowering the contrast size. So here it's like very like there's a better difference between these things than the top image. And so if we go back to the image of the baby, these look very similar. So you can apply these sorts of things to any form of image, right? You might want to have more fine grained control. So instead of using these relatively large values like 128, you can do more fine grained raising and lowering of contrast or darkness of the image for any sorts of applications. Anybody want to talk more about this or? No, okay, cool. So the next thing now, these are going to be running some more established algorithms in computer science. The first one we're going to talk, or I guess the one we're going to talk about is removing the background from an image. So you can imagine if we have this image of the Arib building, we want to put Arib somewhere else. In this case, we're going to try to put Arib in space. So what would you need to do to accomplish that? Well, we need to get rid of the sky. We need to get rid of the grass. So the first thing we'll do is run this algorithm called GrabCut. And what this does is it will take a bounding box, in this case represented by this, and then attempt to select the object that's inside that bounding box. So in this case, it's clearly highlighted the boundary of a rebuilding, right? This is the Anton Auditorium. And then we will take a background. So in this case, this is a picture from the James Webb Telescope of the clouds or stars being born. And then we can cut out where we would go in this image, right? So instead of there being, I guess the stars, there's now a hole. And what we'll do is we'll fill that hole with Arib. And so that's what this does. So what you can try is to upload your own images. And you can do a similar process. We'll give you some time to do that if you'd like. So this button on the side here will let you upload 2 images. You can name them whatever you want, and then you can basically replace like this my image name 2 with, instead of space, whatever you called your image, and then you'll replace the background of the Arib with your background. So you can pick dogs or cats or anything like that. I guess we can briefly do that as you do things. So turtles, let's say.
Wait, then you have to select the bounding box.
No, we're just going to replace the background.
Oh, okay.
Okay, so yeah, so if you want to follow along, you can search whatever you want. I'm going to search turtles. I'm going to download this image. Turtles.png. Yeah. Okay, so then once you have an image you like, you can click this little upload button and upload it. Yeah. And then if you double click it, you can see like that's my picture of the turtle. And then where it says space.jpg, you can replace that with whatever you called your file. So I called mine turtles. And now I have a picture of a turtle. So very low res picture, which is why it's pixelated, but that will do the job. And this next cell will subtract out where Arib will be going. So now you can see we have a turtle with a large building shaped hole in it. And now we'll fill that hole with Arib. And there we go. Arib's underwater. And so you can imagine, this is a very toy example we could use for other sorts of things, right? You want to pretend you're somewhere else. You can easily do that with a person or other objects. Yeah. How do you what? Yeah, great question. So so looking at this, right, there's 2 axes here and with number values. And so the idea is you want to put like the pixel coordinate of the start and then the width and height. So in this case, I picked something that's like roughly here. So like 100 and 100 start. And then the width is like, 700 and the height is 400, 500. And so they're like good web UIs to do this thing too, where you can, select the thing more exact.
Yeah, so the rectangle is defined here.
Right, so yes, first 2 coordinates is your top left corner, and the second 2 is your width and your height. And yeah, this is an algorithm called GrabCut, which is a relatively old technique. If you're from, there's lots of new things. So the one you might want to look up is called Segments Anything by Facebook, and that will let you do a lot more forms of like clicking around to get these sorts of maps around an object. Yeah, so that is like a cool little thing you can do with code, very simple, and just a few lines of code. And the last thing we'll briefly touch on is we talked about how there are multiple channels to a color, right? Humans perceive things in color, not RGB or not grayscale. And so the idea is that these images are actually 3 2D grids of pixels. And so you can access them by doing this little fancy syntax. If you're familiar with Python, it's very obvious, but if you're not, very confusing. These brackets mean go to like these cells. And the first thing that this little colon means everything. The second colon means also everything. And the last one means the channel. So in this case, it's saying get all the pixels in the X direction, get all the pixels in the Y direction, and then get the ones corresponding to red, green, and blue. And so here, the way this is set up is you can now provide your own math functions individually to every function. So in this case, we multiplied the red channel by 2, and so we boosted the contrast of the red channel. So hence the array looks way more red than it did before. So you're welcome to like try out different math functionalities here.
Yeah, if you do something like multiply the green by 2 instead, it's going to look more green. Yeah, like that.
So this is cool for fancy effects and stuff. And another interesting thing this is used for is if your image might artificially be deficient in some color or have like more of one color. So for instance, if you're at like a party with a lot of like red lights or different color lights, then you might want to adjust those things so it looks more normal afterwards. Or maybe you want to make it look as if you're at a party when you really weren't. So you're gonna affect these things. Yeah, so people, you can play with this. This notebook is available for you to kind of play with things. But I guess we'll briefly talk about a few of things. I guess anyone want to talk about this demonstration at all? Or have any questions? Cool. Okay, so then I guess the last thing we'll talk about is some more interesting things in computer vision. So the big one is image generation from text. So you can imagine that you have some prompt and you want to generate. So instead of taking a picture yourself, you want to have the computer automatically generate a picture of that. This has been very popular in the last few years. You might have seen news articles about this. This is kind of like ChatGPT, but for images. So for instance, on the very first slide, I can say, a photo of a Victorian house, and that might produce this nice looking house here. But now you might want to transform that into something else. You can, do things like convert it to a photo of a modern house. And so you can see that there's like a progression to these different forms of things. And there's other things, right? Lion to a cub, and same thing with the types of seasons. And so, well, briefly how this works is basically starting with noise. And so you have a really, really noisy image and then slowly unnoises the image to add these new features. And so that's why when you enter in a prompt, it can give you lots of different suggestions because it's starting from a random thing in the beginning and, generating some nice looking thing at the end. So if you want to try, or I guess some other applications that this can do are things like inpainting. So in this case, this might be the opposite of what you want, but you can imagine you have this person, but you really wanted the picture of the fence. And so you can now select the person and say, fill this in with a fence. And similarly with the bench. And you can also do the opposite, right? You might have like a doppelganger in the background that you want to get rid of. So there's a lot of websites you can try on your own. The one that you might want to look up is called Stable Diffusion. There's a link up here where you might be easier just Google Stable Diffusion. You can also like Google text to image, and there'll be a bunch of different things. And the idea is you can enter a prompt. So in this case, I said a turtle riding with friends, and it produced these two things. You can be the judge of whether or not this is actually a turtle riding with friends. Your mileage will vary of how good these are. And some interesting things here, you can also enter, instead of entering a positive prompt, you can enter a negative prompt. So you could, for instance, say things like you don't want it to be something. So you maybe you're trying to generate a picture of somebody's body and you want to say like no missing limbs, or maybe you don't like, you're trying to create a pet, but you don't want it to be a cat. So you can say person with a pet and then put cat in the negative prompt. And so kind of guide it in some way. So that's like all we have. We can talk about some of these things in more detail if people are curious about something specific. But otherwise, that gives you a brief introduction to how you can process images using Python and code, and hopefully shows you some more interesting things you can do as you develop your skills here. Yeah, sure. Yeah, go ahead. Yeah. If you're just a beginner in Python? Yeah, so a lot of things. So the nice thing about Python is it's much more friendly than a lot of other languages. So you can treat this notebook as like a kind of guide to how to do things. And there's a ton of tutorials on how to go through it. But the big thing that Python has as a leverage is a large source of libraries, right? So this grab algorithm here is like probably many lines of code for you to implement yourself. And this is just one line of code right here. You just call the function here and you can do it. So the big thing to do is look at these different libraries. The main ones are like OpenCV and Pillow that lets you manipulate images in a way, and you can kind of stitch these things together to produce things, right? So this whole section is basically stitching together functions to accomplish these goals. And I'd say like, yeah, it's very you can ramp up very quickly with Python, I think. Yeah. Yeah, so if you want to go to this link, tinyurl.com/DIY Photoshop, or scan the QR code. And then click copy to drive to make a copy of that.
So once we have the pictures changed in a different ways that we can do it with Python, can we download them in order to have to print them or something?
Yeah, you can save these images too. So in this case, I guess we can talk about that. We're using this like Matplotlib is a library used to visualize things, but you can also save these images. So for instance, let's say I want to save the darkened image. So I can say like dark equals darken. And then using the CV function, you can do cv.imWrite.
Be careful, like BGR and RGB.
That's true. Okay.
This is plt.mz.
Okay. Yeah. Okay. Yeah. So okay, we'll do pld.mz.
Yeah.
Dark. And I think you perform it here.
I think path might be first, but we can try both.
Yeah. Test.
Oh, you have to find what
Let's see. Okay, this is a lot more work than it should be. But... Okay, so now if we go to sync. So now this is the darkened image. So to describe what happened here is we use this library called matplotlib. We called the imsave function on it. We said where to save it to. And then all of this is basically to convert it into something the library likes. And so what this is doing is saying, make sure we only have values from 0 to 255, because as I mentioned before, that's how images are like to be stored. And the last thing is saying, interpret that data as these uint8s, which are bytes that the image will use. Otherwise, it'll treat it as some other data format and do some weird things. But yeah, so this is what you can do to save things.
So download it.
Okay, and we can also download here. So if you do right-click download, then it'll put it onto your desktop. And now I have it to share with everyone. Okay, there's another hand over here, I think. No? You had a question? Yeah.
Recording is to be posted.
Yeah, and you can we can make the slides available, but yeah. Yeah, I guess, yeah, the slides also have a lot of other information about we go into depth of how light works and, why you need lenses and things like that if people are interested, but it's a lot of information, so. Yeah. Any other questions or comments or concerns? Yeah. I personally have not taken it, but I'm sure.
I've TA'd it before.
There we go.
So. Yeah, I think they cover some of this stuff in the class, but they also cover a lot more. I mean, this is more like image processing. There's also computer vision covers stuff like 3D structure estimation, figuring out how far things away are. So that's a little different from this, but yeah, stuff like this is also included there. Yeah, well, I think we're
cool. Well, I think that's it. We can stick around for a few more minutes if people want, but you're also welcome to leave. You're not hostages, so. Cool. Yeah. Yeah. Oh yeah, I can put this link actually in here.
Oh, but then they have to recopy this thing, right?
That's okay. Actually. Okay, if you refresh, the links are there. Cool. Well, thank you all for coming. Hopefully you're inspired to do more image processing things in the future. We think it's really cool. Yeah. Yeah, we can briefly go through them if you'd like. Sure. So yeah, so there's this thing called optics that are pretty cool. So you can imagine if you just have a sensor and you have a real world object, we can imagine what it would look like for the image to capture it. So what happens is you can imagine that rays will bounce off in all directions from an object. So one ray will go parallel, like directly to the sensor, but there will also be all these other rays. And for the other side of the tree will also be the same. So if we take an image like this, it'll produce something really blurry, right? No one wants to look at this. So there's this idea of a pinhole where if you put a barrier in here, now only certain direction rays will hit it, right? All these other rays are blocked, and same thing from the other direction. So if you take an image like this, it'll produce more, it'll be a sharper image because each part of the scene only corresponds to one image or one point in the pixel, right? So it'll look something like this. So there's a problem here, which is that although the image is really sharp, you're blocking a lot of the light, which isn't good if you're in like low light scenarios. So the idea is but if you make the pinhole larger, now more light will get in, so you don't have these issues, but now it's more blurry, right? The tree is not as good. So a lens fixes this problem by basically focusing the rays that come from different directions to one point in the image. And then on the sensor side, we'll skip that. I guess like this is kind of how a sensor works. There's a bunch of like photodielectric effects, which is basically every time a photon comes into the sensor, it spits out an electron. It loses some efficiency, but those electrons get accumulated in these buckets that we talked about, and it gets converted to a signal. So I guess this is, in practice, you have different filters. So you say like red, green, blue, and you a bunch of these, every time light comes in, light will be blocked based on its wavelength. And if it hits its right wavelength, they'll get into these like little wells, and those will fill up over time. And yeah, those things are what converts it into electrons using this photoelectric effect. And yeah, and then the way these pixels are laid out, it's called the Bayer pattern. So it's a checkerboard of green, red, and blue. And the idea is then you can convert that into the 2D grids that we talked about before. Yeah, and then I think we talked about the rest. Yeah. Yeah. Yeah, that's like